All right, welcome, folks. In this lesson, I'm going to be concluding our discussion with methods of solving second-order linear differential equations. There's a couple more methods I need to discuss when solving variable coefficient second-order differential equations. And they talk about the Cauchy-Euler method and using another method called reduction of orders. So let's get started. So here is what a Cauchy-Euler equation looks like. So a linear second-order equation that can be expressed in this form, right? A times t squared times y double prime of t plus b times t times y prime of t plus c times y equals f of t, where a, b, and c are constants. This is what's called a Cauchy-Euler equation, or it's what's called an equidimensional equation. Equidimensional refers to looking at how we can reduce down a order of a differential equation. So, and I'm going to go over the overview of the solutions of the Euler Cauchy-Euler equation. So, like finding solutions for any different, for any differential equation, we take a guess. So let's suppose y1 of t, right? Suppose that our solution looks like this, t to the r power, right? Instead of y1 of t, I want to just say just y of t. So suppose our solution, y of t, just looks like this, right? Then if we differentiate y, so y prime of t, this is r times t to the r minus 1, and then y double prime, so equal to r times r minus 1 times t to the r minus 2, right? T to the r minus 2. So if we plug these functions into the homogeneous equation of this type, so the homogeneous would be at squared y double prime plus bt y prime plus c times y is 0. Okay. So we're supposing that these functions satisfy the homogeneous equation. So if you plug it into this equation, we'll have a times t squared times this quantity r times r minus 1 times t to the r minus 2, right? Plus b times t times r to the t raised to the r minus 1 power. So let me erase this here. Plus b times t times r, gosh darn it, r to the t raised to the r minus 1. And then plus c times t to the r power, which is 0. Okay. Now, if you notice, things simplify a little bit. So t squared will cancel with the power of the t to the r minus 2 power. And then also the t to the r minus 1 will cancel with one factor of t here, and we'll have a singleton t to the r for the last term. So what this turns out is, so we'll have a times r minus 1 times t to the r power plus br times t to the r power plus c times t to the r power, right? Which is 0. And if we factor to the t to the r power, we'll have a times r minus 1 plus b times r plus c is 0, okay? So the only way that this quantity here is zero is if, well, t is zero or this quantity is zero. So this here is important. So we're going to look at where the r's are zero in that quantity. So we'll have a times r minus 1 plus b times r plus c is equal to 0. So we're going to look at the roots of this quadratic polynomial and looking at where this quantity would be 0. So this is the characteristic equation that we're going to be using here. I spelled that wrong. So characteristic equation. CHARACTSTIC. So this is the characteristic equation in that case in interest here, right? So now, so we're going to have two cases. If R has two distinct roots, right? So if R1 and R2, let's say, are roots of the this equation, A times R times R minus 1 plus B times R plus C is 0. Okay. Well, the easy case is if R1 does not equal R2 and they're both real number components, right? So if they are real, then we'll have two distinct solutions, right? So we'll have y1 of t is equal to t to the t to the r1 power. Excuse me. So I meant t to the r1 power, and then the other solution is t to the r2 power, right? And the only idea, and the thing we have to test is if y1 and y2 are a linearly independent set of solutions, right? And you can check this by computing the Wronskian, right? The Wronskian. Okay, so let me erase this piece right here. Right, so the Wronskian, excuse me. Right, so t to the r1, t to the r2, and then this is r1, t to the r1 minus 1, and r2, t to the r2 minus 1, right? And then figuring out the determinant of that matrix, so we'll have r2, so, and t raised to the r1 plus r2 minus 1, right? And then minus r1 times t to the r1 plus r2 minus 1, right? I mean, the only way this is 0 is if t is 0, obviously, or r1 equals r2, right? So if we're assuming that r1 is not equal r2, this is linearly independent, right? So if they're distinct, that's the straightforward case. Now, if we have a repeated root, a repeated real root, right? So if R1, so this is the first case. The second case is if R1 does equal to R2 and it's a real number, right? And then we're going to have one solution. So if I let this equal to R, so we'll have t to the R, and then y2 of t is equal to t to the R times ln of t. Okay, t to the R times the natural log of t. And to get this solution, you're going to use a method called the reduction of order method. And I will explain that much later in this video, right? So, so using reduction of order, this this would be the two set of solutions if we have a repeated root for this quadratic equation. Okay. And also for the complex roots. So let's take a look if the other case. The other case is where the quadratic equation has two complex roots. Okay. So the other case is if R is equal to two complex roots, alpha plus I beta. So we have y of t is equal to t to the alpha plus or minus I beta. Okay. Right. And so, and we're going to use the same strategy of figuring out two set of solutions for a second order differential equation. Right. So we're going to have y1 of t as t to the alpha times cosine of beta times ln of t. And then y2 of t is t to the alpha times sine of beta times ln of t. Now, why is that the case? So if I look at, let's say, this quantity, right? T to the alpha plus I beta by properties of exponents is t to the alpha times t to the I beta. Okay. And so by using another property of exponents, t to the alpha times t to the I beta, this is equal to t to the alpha times e raised to the natural log of t to the I beta power. Okay. And so this quantity right here would equal to, this would equal to t to the alpha times e to the I times beta ln of t. And then you're going to use the Euler's identity. So t to the alpha cosine of beta ln of t plus I times t to the alpha times sine of beta ln of t. Okay. And then the other solution is when y2 is equal to t to the alpha minus I beta. Okay. And then you're just going to use a linear combination of the solutions of the differential equations generated by alpha plus I beta and alpha minus I beta here to get these fundamental solutions here. Okay. So that's sort of the overview of the type of solutions for a Cauchy-Euler equation. So, yeah, so I did that. So an overview. So the solutions is if this equation here has two repeated roots, R1 and R2, if they equal to the same number, then these are your two fundamental set of solutions. Y1 equals t to the r power. Y2 is equal to t to the r times ln of t. If this equation here has two complex roots, r equals to alpha plus I times beta, I times beta, y1 is equal to t to the alpha times cosine of beta times ln of t. And then y2 is equal to t to the alpha times sine of beta times ln of t. The one I didn't include is if this characteristic equation has two distinct real roots, right? Then y1 of t is t to the r1, and then y2 of t is t to the r2 power. Okay, so it's probably straightforward. Let's look at an example. So here's an example. We want to look at how to find a general solution for the following differential equation. 9t squared y double prime of t plus 15 times t times y prime of t plus y of t equals to 0. Okay. First of all, if you recognize, this is a Cauchy-Euler equation. Cauchy-Euler equation, right? So we want to label out what the A number is. So the A is 9. The B number is 15. And the C number is 1, right? So the characteristic equation, this will be 9 times R minus 1 plus 15 times R plus 1 is 0. So we have to solve for R in this equation. So we'll have 9R squared plus 6R plus 1 is 0. Okay. This here is factorable, right? So ask yourself, what are two numbers so that their sum is 6 and their product is 9 times 1, which is 9. So it's 3. So what I'm going to do is replace this middle term with a sum of the factors of 9 that add to 6. So in this case, it's 3R plus 3R. And then I have a plus 9R squared here, and then a plus 1 here, right? And then we're going to do a factoring by grouping method. So these first two terms, you can factor out a 3R. So 3R. So this is a 3R plus 1. And then this here is just 3R plus 1. The last two terms will be 3R plus 1. So it'll be 1 times 3R plus 1, right? And so if you notice, this is equal to, so 3R plus 1 squared. So we have a repeated root. So therefore, R is equal to negative 1/3 with multiplicity 2, right? Multiplicity 2. So what that means is y1 of t, this will equal to t to the minus 1/3, and then y2 of t is equal to t to the minus 1/3 times natural log of t. Okay. And so the general solution, C1 is t to the minus 1/3 plus C2, t to the minus 1/3 times the natural log of t. Okay. Times natural log of t. Okay. And so that is one example. And then the last method I want to go over is what's called reduction of order. So let's go over the method of using reduction of order. So y1 of t is a general solution to, so y1 of t is a general solution for this homogeneous equation. So in the textbook, right, they are referring to a variable coefficient differential equation to be this, where the coefficients of the second order differential equation are functions of t, right? I should say f of t here. No. Okay. So what I meant here is, so this is equals to a function f of t, right? F of t, sorry about that. So, and if you divide both sides by a of t, well, we'll just get this formulation on the left, right? And they're assuming y1 of t is the solution for the homogeneous equation, right? So, right, so y double prime of t plus p of t times y prime plus q of t times y equals just another function of t, g into t, right? And then they're supposing y1 of t is a solution for the homogeneous equation. Okay. So now, so I is an interval where p of t and q of t are continuous functions, right? And so the idea is this: we want to suppose that a function y of t equals to a product of v of t times y1 of t. Okay, so get this out of the way. So we're going to assume that y is equal to v times y1, and then y prime, this equals to the product rule. So v prime times y1 plus v times y1 prime, and then y double prime. So we have to use the product rule twice. So this is v double prime y1 plus v prime y1 prime plus v prime. So v prime y1 prime plus v prime y1 prime plus v y1 double prime. Okay, so that's the second derivative of y. And if I plug that into the equation, so in the differential equation, so we'll have y double prime is, so I'll have v double prime times y1 plus, this is two of the same quantity. So 2v prime y1 prime plus vy1 double prime plus p of t times y prime of t. So v times y1 prime plus v prime times y1 plus q of t times q of t times y of t. So v times y1 is 0. Okay, so right away, we can see what is going to happen. And so what's going to happen is, so we'll have, so we have this quantity here plus p of t times this quantity plus q of t times that. So if I gather those terms up, so I'll have v times y1 double prime plus p of t times vy1 prime plus q of t times vy1. And each of those quantities have a v in it. So if I factor out the v, just a minor touch. So if I factor out the v term, so that's time, shoot. Keep in mind, this is equals to 0. Right, this, so y1 is a solution for this differential equation, right? So what that means is, that, oh, Jesus Christ. So what that means is that this quantity is 0, right? So that's 0. And so what's left over are this factor, and p of t times this factor. So we'll have a v prime double prime times y1 plus 2v prime y1 prime plus p of t times v prime y1, right? And so if I erase this, so I want to rewrite what I have here. So 2v prime y1 prime plus p of t v prime y1 is 0. So if we have this as our solution, so I'm going to get rid of this work here. And so, oh, come on. And so, now, what we're going to do is apply a substitution. So, what we're going to do is we're going to let W equal to so we're going to let W equal to V prime. Okay, then that means W prime equals to V double prime. V double prime. And so by applying this substitution, so in W's, this equation will turn out to be, well, this is W prime times Y1 plus, so we'll have a 2W Y1. So, okay. Y1 prime plus P of T times W times Y1 equals 0. And so this equation would equal to Y1 W prime plus, so we'll have a W Y1 prime plus P of T times Y1 equals 0. This here is a first order separable differential equation. And then we can get to solving what W is. And therefore, it's back substituting to get the other general solution. So once we back substitute, we will get the second solution for y2 as y1 times the integral of the integrating factor. So in this case, this is the integrating factor. Okay. Over y1 squared times dt. So this is the second solution to get by using this reduction of order method. Right? So let's look at this example. So we want to figure out a second linearly independent solution using the reduction of order method. Okay, for this differential equation. T is positive. Okay, and this is actually what y1 of t is, right? So the formula again, so this is y1 times the integral of e to the minus the integral of p of t dt over y1 squared dt. Y1 squared dt. Okay. So if we know y1 is 1 over t, essentially, okay, y2 y2 is equal to 1 over t times the integral of e to the minus, so P of t is this quantity. So P of t is e to the minus 2t. E to the minus 2t dt. Over 1 over t squared dt. So this equals to 1 over t times the integral of, in this case, t squared e to the 2t dt. All right. And so this equals to 1 over t. And we're going to use tabular integration for the t squared e to the 2t quantity. So let me do that real quick. So u and then dv, t squared t1, 0. And then we'll have 1/2 e to the 2t, and this is 1/4 e to the 2t, and this is 1/8 e to the 2t, right? And then with tabular integration, we're going to multiply diagonally. So you have to multiply t squared by 1/2 e to the 2t, and then we add those quantities. Then we subtract the product of t times 1/4 e to the 2t, and then we add 1 times 1/8 e to the 2t. And so what this quantity will equal to is 1 over t times t squared over 2 e to the 2t minus t over 4 e to the 2t, and then plus 1/8 e to the 2t. Okay? 1/8 e to the 2t. And so this is equal to e to the 2t times t over 2 minus 1/4 over 8t. So this is y2 of t. So that's the other linearly independent solution. Okay? So that about does it for solving different second order differential equations. Okay? And then what I'm going to move forward next is a method of using Laplace transforms. So we're going to get right into the good parts of differential equations. But for now, here's some problems for you to check comprehension. This is so these sets of problems here. This is just straightforward review for variation of parameters. And some of them involve variable coefficient equations, but the strategy is the same, right? So figuring out what y1 and y2 are, using those methods, right? This will cover the Cauchy-Euler equations, and these sets of problems deal with reduction of order. Okay. So in the next video, we'll talk about Laplace transforms. So hope to see you then. Thanks for watching.